Yesterday, you guys looked at some counting principles where the order was important. So you looked at how many arrangements you could make when given so many objects and choosing, five of those 20 people that cross the finish line, how many different ways could they come in first, second, third, fourth, and fifth place. And in those problems, we were trying to arrange them where our order was important. And when order is important, we use a permutation. And we had our formula for that where we said that if we want to find the permutation of n objects taken r at a time, that we take the total number factorial and then divide it by n minus r factorial. So in this case, we counted up all the different scenarios. So again, runner A, B, C, D, E crossing the finish line in order was different than B, A, C, D, E crossing the finish line. But today what we're going to look at is a method where we're selecting subsets of a larger set where order is not important. So now we're looking at some scenarios where it doesn't matter how the objects get chosen. So if I have a bag of 20 marbles and I choose 3, it doesn't matter the order in which I select the 3 marbles. So a selection of red, yellow, and blue would be the same as a selection of yellow, blue, and then red marbles. So what we need to do is adjust our formula so that we can take out those duplicate combinations of the same elements. And that's where our combinations come into play. So when we're looking for an arrangement where order does not matter, we're looking at a combination. And it's going to have a very similar look to it. So we're going to have a combination. We're going to use the letter C to represent combination of n elements taken r at a time. And you're going to notice the formula starts out looking exactly the same as our permutation formula. We have n factorial in the numerator, and in our denominator, we see that n minus r factorial. But to take out those extra duplicate sets, we're going to also, in our denominator, include r factorial. So very similar to what we did yesterday, but this time we're taking out duplicate combinations so that we have a smaller subset of values here. So we're going to look at 3 word problems to kind of show how we use this formula. So the first example says, in how many different ways can 3 letters be chosen from the letters A, B, C, D, and E? So notice it's not saying that they have to be in a specific order. A lot of times you might say that 3 letters be, sometimes you might see the word randomly. When you see the word randomly, that also means that order doesn't matter. So when the order doesn't matter, again, selecting A, B, and C would be the same thing as selecting B, A, C, or C, B, A, things like that. Now, I could make a list of all the possible combinations, but for this problem, we're just going to jump right in and use our formula. So we're looking at a combination because order doesn't matter. We have 1, 2, 3, 4, 5 given letters, and we want to choose 3 of them. So I'm looking at a combination of 5 choosing 3. So to set up my fraction, I'm going to put in my numerator 5 factorial. In my denominator, I'm going to take 5 minus 3 and get 2 factorial, and then I'm going to multiply by that r. So my denominator is going to be 2 factorial times 3 factorial. And these 2 numbers should always add up to be your total set. So then when we're simplifying these factorials, again, I'm going to take my larger factorial and expand it down until I match up with the larger factorial in my denominator. So I'm going to expand 5 factorial as 5 times 4 times 3 factorial. That'll match up with the 3 factorial at the end. And then I'm going to actually expand 2 factorial, which is really just 2 times 1. So for this one, I have 5 times 4, or 20, divided by 2, and 20 divided by 2 is just 10. So there are 10 ways that I can choose 3 letters from that set of 5. So very similar to what we did with our permutations, but again, we're taking out duplicate sets. In another example here, we have a standard poker hand that consists of 5 cards. So as they're working through the game, each person's going to eventually be dealt 5 cards from a standard deck of 52. So each player is going to get 52 cards, 5 cards from that set of 52. And we want to know how many different poker hands are possible. Now this is going to end up being a combination because, again, order is not going to matter. Once a player is dealt their cards, they can take their hand and rearrange it. So in other words, if they're dealt 2 tens, a jack, a queen, and a king, they could rearrange that however they want. Maybe they're going to match up their red cards together and their black cards, things like that. But after the cards are dealt, a player can reorder them. So in this case, order does not matter how it's handed out. So that's our symbol to use a combination. Again, we're going to take our n factorial. So our total number of cards for this was 52. Then we're going to take 52 minus 5 and get 47 factorial for the n minus r. And then we're going to multiply by r factorial down there. Again, I'm going to expand the larger factorial, in this case that 52, until I get to that larger factorial in my denominator of 47 factorial. So I'm going to take 52 times 51 times 50 times 49 times 48 times 47 factorial. That's going to match up with that 47 factorial down there. And then I'm going to expand the 5 factorial as 5 times 4 times 3 times 2 times 1. Now at this point, you really have 2 options. You can go take out your calculator and multiply all the numbers in your numerator, and then multiply all the numbers in your denominator, and then find those 2 values and divide. Or you could start simplifying. So I know that 4 goes into 48 12 times, 5 goes into 50 10 times, 3 goes into 51 17 times, and 2 goes into 52 26 times. So I could simplify this way and then just multiply my remaining values. So 26 times 17 times 10 times 49 times 12. All those remaining values would give me 2,598,960 different possible poker hands that could be dealt. Again, if you don't want to have to simplify like that, you could always just multiply straight across, and divide. You will get the same answer. My last example is a scenario where you might have to do a combination more than one time. So depending on what we're looking at, sometimes you might be choosing subsets of a more than one set of objects. So in this case, we have a 6-member research committee, but it's going to be formed by having 1 administrator, 3 faculty members, and 2 students. So when I'm looking at this here, I have my administrator set that I want to choose and figure out how many ways can I get an administrator. I need to get some faculty members on this committee. So I have to figure out how many ways can I choose faculty members, and I can also get students on this committee. So I have to figure out how many ways can I get students. Now the order that they get chosen doesn't matter. So if I choose administrator A then B versus B then A, there's still going to be the same 2 administrators on that. Same thing with the faculty members and the students. So for this right here, they're all going to be a combination. So from the administrator, I want to choose 1, and there are a total of 7 administrators to choose from. So we're going to have 7, combination of 7, taking 1 at a time. For our faculty members, we want to get 3 faculty members, and there were a total of 12 on this school there, or college. And then finally, we need 2 students, and there were a total of 20 that were possible candidates for this committee. So what I'm going to do is evaluate each of those combinations separately. So for my administrator, I'm going to have 7 factorial over 6 factorial times 1 factorial. When I expand that out, it's going to give me 7 times 6 factorial. My denominator is going to be 6 factorial times just 1. So there are 7 different possible administrators, obviously. If I'm only choosing 1, I can only choose 7 out of those guys. For my faculty, I have 12 and I'm choosing 3. So I'm going to do 12 factorial over 9 factorial, 3 factorial. 12 times 11 times 10 times 9 factorial in my numerator, 9 factorial, and then I'm going to expand 3 times 2. So I have 12 times 11 times 10, and then divided by 3 times 2. So again, I could either multiply straight across the top and then divide, or I can simplify. 3 times 2 is 6. That's going to go in there 2 times. So 2 times 11 times 10, there were 220 ways I could choose faculty members. And then finally for my students, I have 20 students and I want to choose 2. So I'm going to divide by 18 factorial times 2 factorial. I'm going to expand that numerator until I get to 18 factorial to match up with that 18 factorial. And then I'm going to expand that. I get 10 times 19, so I have 190. So now I know that there were 7 ways that I could choose administrators, 220 ways I could choose faculty members, and 190 ways that I could choose students. To get the total ways to create the committee, all I have to do now is multiply all of those sets together. So if we take 7 times 220 times 190, we find out that there are 292,600 ways that this committee could be formed. Okay, so as you're going through, what you're going to work on are finding some combinations using some word problems similar to these. Some of them you might only need to use the combination formula once, and some of them you might have to use them twice. If you have any questions, feel free to reach out.